In this video, I'm going to discuss binomial expansion. Now, before we look at binomial expansion, first of all, we need to understand what a binomial is. Now, a binomial is a mathematical expression with two terms. For example, A and B. And the two terms will be A and B. And an example of a binomial expression will be something like A plus B to the power of n. And what we want to find out is what happens when you multiply a binomial by itself many times, for example, n times. For instance, when n is 0, we have a plus b, a plus b to power 0. Now we know that anything to the power of 0 is 1. So basically, this will be equal to 1. How about when n is equals to 1? So if we have a plus b to power 1, that will just be equal to a plus b. How about if we have a plus b squared? Now, we know that a plus b squared will be equal to a squared plus 2ab plus b squared. How about if we have a plus b cubed? What we may have to do here is to multiply out a bracket, because we know that a plus b cubed is the same as a plus b multiplied by a plus b squared. Now, a plus b squared is the same as a squared plus 2ab plus b squared. And if we multiply this out, we'll end up with a cubed plus 2a squared b plus ab squared plus a squared b plus 2ab squared plus b cubed. Now here we have like terms that we can simplify or we can group. So what we'll end up with here is a cubed plus 3a squared b plus 3ab squared plus b cubed. So that's the expansion of a plus b cubed. And we can write it here. So a plus b cubed will be equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. How about a plus b to the power of 4? Now, a plus b to the power of 4 will be equal to a plus b multiplied by a plus b cubed. So basically, a plus b multiplied by the result that we have above here, which will be a cubed plus 3a squared b plus 3ab squared plus b cubed. And if we multiply this brackets out, we shall end up with a to power 4 plus 3a cubed b plus 3a squared b squared plus ab cubed plus a cubed b plus 3a squared b squared plus 3ab cubed plus b to the power of 4. And we can group the like terms. So we'll end up with a to the power of 4 plus 4a cubed b. That is if you have this one and this one grouped together. So you have 4a cubed b plus 6a squared b squared, because you have that and that one grouped together, plus 4ab cubed plus b to the power 4. So we can write our result here. So we'll have a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. Now we can notice a couple of things here. Let's try to pay attention on the coefficients. Let's try and focus on the coefficients. Now here the coefficients are just 1 and 1, and here the coefficients will be 1 and 1 as well. So you have 1, 2, and 1. And here the coefficient will be 1, 3, 3, and 1. And here the coefficients will be 1, 4, 6, 4, and 1. So if I just highlight them, that is the coefficient for a plus b to the power of 0. These are the coefficients for a plus b to the power of 1. These are the coefficients for a plus b squared. And these are the coefficients of a plus b cubed. And these are the coefficients of a plus b to the power of 4. And what we want to do now is we want to consider only the coefficients for the expansions and to try to find a quicker way of generating other coefficients. So that's what I'm going to do next. And if you notice here, 1 plus 1 will give you 2, 2 plus 1 will give you 3, 2 plus 1 will give you 3, and so on and so forth. So that's what I want to consider next. So we want now to consider only the coefficients for expansions, all right, in the previous page, the first page that we looked at, and try and find a quicker way of generating other coefficients. Now, remember at the top, we started with 1, and then what followed was 1 and 1, and these are the coefficients for a plus b to the power of 1. Then a plus b to the power of 2 had coefficients 1, 2, 1. Okay, these are just the coefficients, remember? And then a plus b to the power of 3, we had 1, 3, 3, 1. And then a plus b to the power of 4, we had 1, 4, 6, 4, and 1. Now, you may notice that each term is the sum of the two directly above it. Okay, so if you add these two, you get that. If you add this, you get 3. If you add this, you get 3. If you add that, you get 4. You add that, you get 6. You add those two, you get. So, and just before I continue that pattern, let me label each of these so that you can know what's happening here. So these were the results for when n was equal to 0. I'll call that row 0. And this were the coefficients when n was equals to 1. Let me call that row 1. These were the results when n was equal to 2. The coefficients when n is equals to 2. Call that row 2. And then this was n is equals to 3. Call that row 3. And then these are the coefficients when n was equal to 4. Let's call that row 4. And we can continue with this pattern. Remember, we can actually generate the coefficients when n is equals to 5. Okay? Because all that we have to do is we add these numbers above those that we want. So basically what we'll end up with is 1, 5, 10, 10, 5, and 1. And those will be the coefficients when n is equals to 5. Okay? So there are a couple of things that I've said that I want to write down as key points. So The first thing is, notice that each term is the sum of the two directly above it. And another thing is that um, Pascal's triangle is basically this array of numbers. Okay, so this triangle that we have here is what we call the Pascal's triangle. Okay, so basically what I'm saying here is this triangle of numbers that we have generated here, which are actually coefficients in binomial expansion, are what we call a Pascal's triangle. And we use Pascal's triangle, okay? So we use these numbers to generate coefficients when the power is not too high, because you can see that suppose the n was equal to something like 20, okay, or 15. To generate all those coefficients will take almost a whole page. So there are limits. There are limits when we can use Pascal's triangle. So what we are saying here is that use Pascal's triangle when one when the power is not too high. Okay, so when the power is not too high. And usually these are the kind of questions that will be given non-calculator section of your exams anyway, when the power is not too high. That way you can be able to use Pascal's triangle, because you have to write it out manually. Yeah. Two, if you have to find all the terms in a binomial expansion, okay? Remember, if you have to find all the terms, then the power cannot be high. Yeah. So when you have to find all the terms in a binomial expansion, you can also use Pascal's triangle.